We are Tamu Advanced Robotics Manufacturing, and this is the Los Alamos Capstone project. Giggle. Boom. All right, now let's go inside.
From the 1940s until 1987, the Hanford site in the state of Washington was used to produce plutonium for use in nuclear weapons. Sometime after production stopped, nuclear waste began to leak from this facility's many storage tanks. It is currently estimated that 80 square miles of groundwater have been contaminated. In addition, the waste has also begun leaking into the nearby Columbia River. Los Alamos National Laboratory is one of the organizations assigned to removing the waste and ending its environmental harm.
The primary constraints and requirements the team had to account for during the design process was to use entirely steel to protect against volatile materials. The vehicle has to fit within a 42-inch diameter. The material removal rate is at least 4 gallons a minute. The vehicle has to be driven on screws and use a ladder excavation type system.
One of the ways Llano has chosen to attack this problem is with capstone programs at Texas A&M. Previous capstone teams have made iterations of the same overall concept, an excavation vehicle using screws for locomotion. The use of screws allows the vehicle to traverse a wide variety of terrains, which is essential due to the toxic waste environment. Tamu ARM is the latest capstone team to develop a new vehicle design.
This design is different in that it features a ladder excavation system, which is used to scoop material and deposit it into a waste container located on the vehicle. The ladder excavator should apply less downward force on the tank, helping to ensure the integrity of the tank and preventing the creation of new leaks. Additionally, the drivetrain is all electric to help minimize weight and improve controllability. This design will serve as a proof of concept for the viability of the ladder excavator and electric drivetrain. If it functions well, Los Alamos may select this design for further development and potentially real-world use in the Hanford waste tanks.
The vehicle fits within 42-inch diameter, which is the size of the opening of the nuclear waste tanks in which the vehicle will be going into.
Howdy, I'm Kyle Broyles, and I was in charge of the ladder excavator system. As you can see right here in the middle, here it is. It's driven by a 40-volt three-phase motor, which is mounted right here on custom mounts and using a custom coupling to mount it axially. It's using 4 homemade buckets right here, which will dig up material from the bottom, bring it up and around, and put it in our waste container in the back. So for adjustability, if you can kind of see it right here, there's these linear actuators which raise the whole system up and down so that whenever you go into deeper material, you can have some clearance right there. And I can showcase the little system working right now. I might have to speed this part up a little bit. It's very slow because it has high gearing to withstand a lot of force. That's going down. And as to hold tension in the chain, I use this center bar right here, which is built on slots so that I can have some adjustability there. And that's my system.
Hi, my name is Bryce Lofton, and this is the Tamu ARM project, and I am in charge of the drivetrain. So starting up here, I'll discuss just how that's all put together. We have 40-volt three-phase DC motors that are hooked up to a sprocket chain drive system that essentially transfers all the power from the small sprocket to the larger sprocket. And then this larger sprocket is attached to the axle down here, and that is welded onto the screw. That transfers all the power. This axle is held up by 2 taper bearings that are facing opposite directions from each other, and so it basically withstands axial forces back and forth. We made custom motor mounts and bearing mounts to hold those together. And what else? There's also retaining rings that are sitting behind each of the taper bearings in order to actually lock the location of those. And here, I'll spin this around so that we can see the front. In the front, you can see the chain drive system better. Again, it goes from up here and just transfers power down to the bottom. We also created chain covers right here that will bolt onto this back mounting plate, if you can see it right here, with 3 long bolts, essentially.
Howdy, my name's Sebastian. I was in charge of doing the screws, designing and manufacturing the screws. So here we have two fully custom made screws using a 6-inch outer diameter tube and carbon steel 1/8 steel sheets. So essentially what we did, we have four full revolutions here on the screw, and to make things more efficiently when welding the actual blade onto the tube, we essentially just water jetted out 5 different revolutions, so we can basically bend it out on the vise 6 inches from here to here, bend it out on the vise 6 inches, and place it on the tube and weld it.
Howdy, my name is Camden Ambrose, and I was in charge of designing the frame. This frame is carbon steel, 1 by 1 inch square tube. One important factor when designing the frame was making sure that all of the components, once they are mounted, they fit within a 42-inch diameter. And so we have 2 mounting sheets on both sides that allow us to mount the motors, batteries, and other electronics. Additionally, in the back here, I designed a waste container so that whenever the excavator system is functioning, it'll just toss waste into the back here.
Okay, I'm Nick Cedillo. I was in charge of the electronics, and then I also kind of became the de facto fabricator. For the electronics, so we pulled these 3 motors out from Ryobi ice augers. So these came with each a 4 amp hour 40 volt battery and these brushless motors. So the initial idea was to be able to control all 3 of these with the PWM system, and so it would give us reverse, forward, and then be able to variably run the excavator. The control style for the vehicle was meant to be somewhat of like a 0 turn. Essentially, we were going to use joysticks to both push forward, both back, go back, and then turn.
This solution incorporates a significant amount of off-the-shelf parts to reduce the amount of custom manufacturing. All of the axles were bought with the correct diameter and a keyway cut in them. All the sprockets, retaining rings, bearings, motors, and linear actuators were purchased. The axles and chains were also designed to be identical across subsystems. Also, to increase ease of manufacturing, the same size sheets were used for both the mounting plates and for the screw threads. And the same size sheets were also used for the excavator buckets and the waste container.
Give a thumbs up, Kyle.
Giggle. With the giggle. Classic.
Stupid ass. Oh, I thought I made it.